Thank you. So in this presentation, we are going to compare the two processes, the acid-bake leach process route and sodium hydroxide roast leach route for extraction of critical elements and variable elements from smelter slag. Okay, so my presentation is divided into six sections. So let's start with the introduction. So we know that copper porphyric polymetallic are major current sources of copper. Now in these deposits, the major variable minerals are chalcopyrite. However, these deposits may contain molybdenite, sphalerite, and other gangue minerals. Most importantly, these deposits may contain critical elements such as gallium, germanium, and indium. By now, we know the importance of these critical elements. We don't have to go into details because they are used in these high-tech technologies. So what happens if these critical elements are recovered together with concentrate and then they are smelted? So this is a simplified smelter or treatment of copper sulfide concentrate. So these critical elements can distribute into three streams. One, they can be lost to the flue dust during smelting. So this can be recovered in the baghouse. Secondly, these critical elements can go to the anode, which are cast in the copper anode. And the last one, these can report and lost to the slag flotation tailings. So this is why we got our sample, and my presentation is about the recovery of critical elements and variable elements from the slag tails. So having given introduction, the objective here is to develop the selective leaching process to recover gallium, germanium, and indium, as well as variable elements from copper slag. Specifically, we are trying to compare two processes. One, the acid-bake leach process route to recover these, and the other one is sodium hydroxide roast leach route to recover these critical elements, and then compare which one will be more effective. Having now given introduction, let me move to materials and methodology. So we collected the sample, and then when we analyzed, we found that it contains around 11.2 ppm of gallium, 7.8 germanium, and 6.5 indium. As you can see, the concentration of these critical elements are quite low, so to make it more viable, we have to also consider recovery of other valuable elements such as molybdenum, copper, and cobalt. But we should be mindful that it contains a high amount of iron, so we shouldn't, the process should not dissolve more of iron, as this can be a burden to the downstream process. It also contains silicon. You know that silicon is a notorious element that can form silica gel during the process, so we should be mindful of that when you're trying to come up with the process. So when we're trying to look at the mineralogy, we found that the major minerals are hedenbergite, firelite, and iron oxide. This was also confirmed by the SEM analysis that we did. So it means that the critical elements and variable elements that we're looking for in these materials are either associated or encapsulated with these major minerals. Therefore, we should find ways of decomposing these minerals. So we developed two methods that we are comparing now to decompose these two minerals, these three minerals. One is acid bake. So using concentrated sulfuric acid, we make a paste, and the idea is that during the process, the minerals are going to decompose to form sulfate salt, and then Si, which is a silicon, it will remain as SiO2, and then this can be leached. The other route is to use now sodium hydroxide. During the roasting, the major minerals can decompose and form sodium elemental oxide. And then the idea is that now the roast product and the baked product can be leached in water or just using weak acid or weak alkaline solution so that you can recover these variable elements. So the method it's similar. So we get the copper slag tails mixed with concentrated sulfuric acid, predetermined amount, and then make the paste, roast it at different predetermined temperature, crush it, and then leach it, and then try to check the leaching efficiency using the formula shown here. For sodium roasting, similar process was used, but in this case, instead of using sodium solution, we used sodium hydroxide pellets. So we mix, we roast it, and then we do the crushing, and then we do the leaching. And again, the leaching efficiency was calculated by using that formula there. So having given you the methodology, now let me go to the results and discussion. So this shows you just the leaching rate of gallium, indium, copper, cobalt, and molybdenum, and iron. I should mention that we had the challenges of analyzing germanium. I'll explain more in detail on that. So the baking condition and leaching condition is as shown here. So what we found when we did baking, we found that actually we were leaching around 71% of iron go into solution. Molybdenum was about around 76% go into solution. Then we have copper, and then we have about almost 60% of gallium go into solution. We have cobalt, about same amount, about 60%. Indium was the least in terms of leaching efficiency, but the notable thing is that the kinetics of leaching of these elements are quite high. Within 15 minutes, we could dissolve this into solution. So here, we find that the high amount of iron going into solution is so high, 71%, and I showed you that it contains about 41% of iron. So this is so high, it can be a burden for trying to recover the critical elements as well as variable elements. So we had the challenges of analyzing germanium, but then when we sent the sample to external lab, we found that actually germanium was not dissolved into solution. And when we dig deeper, we found that this germanium is usually associated with silica. We solved the issue of silica gel, but then we kind of locked germanium into the residues. So we did some optimization. So this just showed you we did trying to look at the effect of acid to slag ratio, baking temperature, solid liquid ratio. What we found out is gallium leaching efficiency increased when you increase the amount of acid to slag ratio and baking temperature. And this speaks to the ease of decomposition of the elements, minerals that I talked about under this condition. And when you increase the amount of baked material compared to the solution, that actually reduced the leaching efficiency, and this speaks to the mass transfer and other things. We found the same scenario with the leaching efficiency of indium. It also affected by these factors. Now, at optimum condition, which is shown to your right here, which is a baking temperature around 350, 1.5 to 1 of acid to slag ratio, and baking temperature of that much. So we found that we can, under this condition, we can leach around 60% of gallium, 40% of indium. And then for variable elements, we can leach copper around 81, and cobalt 87, and molybdenum about 80. However, as I said, we are sending into solution about 71% of iron, which is a burden for a downstream process. So now let me move to the results on sodium hydroxide roast leach. So we did also trying to look at the leaching rate, which are kinetics under those conditions that you can see there. So what we found, gallium under these conditions about 45% leached going to solution. High kinetics as same as acid bake. For germanium, it was somewhere around 41%. For molybdenum, it was high amount, about 80% could dissolve. The goodness of this is that iron remain in residues. That's what we want because it's got a high amount of it. But when we have zinc and iron go into solution, so compared to the acid bake leach and this sodium hydroxide roast leach, this is more selective compared to iron. And maybe you can't see indium here. We could not analyze indium because indium was using an internal standard for ICP-MS, so we cannot report for now. So we're trying now to compare what's going to happen. Maybe I should mention this. We haven't optimized this process, so just on the preliminary. So we did now trying to check if we increase the amount of sodium hydroxide during roasting, what's going to happen to the leaching efficiency. We found that the leaching efficiency increases. And this speaks to, because what this sodium hydroxide does, it increases the amount of OH, and the leaching efficiency of these elements is due to formation of elemental hydroxyl complex. So when you increase the amount of this, it increases leaching efficiency and perhaps increase the amount of decomposition efficiency of the minerals, host minerals. Having given, let me now move to the conclusion of the comparison of this. So what we can conclude so far is that acid bake leach process route kind of prevents the silica gel formation. However, it's got, once we do the leaching, we still have high amount of iron going to solution. And besides that, we have germanium remaining undissolved, which is tied to the SiO2. Sodium roast leach process showed good selectivity of these two critical elements and molybdenum over iron, which is a good thing. However, we still have some impurities that we have to take care of should we go forward the dissolution of small amount of zinc, lead, iron, and silicon. So what we are doing for this, when we do the recovery of these critical elements, we are concentrating actually these variable elements in the residues. So this can be leached using sulfuric acid or other media, which we are going to explore later. So now I can, the references that we used, these are the references. In terms of acknowledgement, we'd want to acknowledge those institutions and those persons that helped us during the processing of that. And thank you. That's the end.
Thank you.